till now in this study we have seen 4 material properties of concern. So, they are in a way you can say the modulus of elasticity E, the bulk modulus K, the Poisson's ratio nu, and the shear modulus G, right. And in an earlier segment we derived a relationship which related the E, K and nu, right. The bulk modulus in terms of E and nu we had derived. And now what we will in this segment what we will do is we will derive a relationship between E, nu and G, and that will complete the setup where we can say then that any two of these 4 material properties if we know everything about the material in a sense of, okay, when I say material, homogeneous isotropic material. So, these 4 values if you evaluate you know everything, okay. So, that means only 2 of them are independent and the other 2 you can always evaluate, you do not have to measure all the 4. Okay. And yeah, so let us do that, and we will do this exercise in 2 different ways. In fact, those 2 different ways will be conceptually also they will involve some different concepts. So, that is why please watch both the videos. I will do that in 2 segments. In the first segment one method, the second segment another method. Please watch both the videos to get a complete picture about though the relationship finally what we will get is the same, but the arguments which are made they will be useful in some other problem solving concepts. Okay. Now, to start with, let us say we have a solid rod like that. Imagine this is a rectangular cuboid and you are applying an axial load of P this side and P this side, okay, the normal axial loading. And then what we do is we will look for the state of stress at a point somewhere on the body, and in order to do that generally we draw or we imagine picking an elemental square, right, for plane stress condition. And in this case obviously in the z direction we are not applying anything, so there will be no stress in that sense. So, instead of a cube we can just think of this rectangle, and then let us think that this square, it is not a rectangle, this square is having 1 unit length on all the sides. But then when you apply the load, what will happen to this rectangle which you have drawn on the body, say. So, what will happen is it will be elongated and it will take some shape like this. It is an exaggerated form, okay, just to make it clear that what shape it will take. And these lengths which the new lengths, what we can tell about them is these are say epsilon x, and because unit length we had taken, and then this length will become 1 minus nu epsilon x, right. So, that is how the rectangle will look like now. Now, what you do, you imagine or either you can imagine at the same location, or you can think that you have got 2 exactly identical rods and identically load conditions, and then you have I will draw another picture. I will try to make it as similar to the above as possible. and there you have P and P, and we are trying to look the state of the stress at the same point, but now instead of drawing this square, elemental squares with sides parallel to the axis or perpendicular to the axis of the rod, we will just rotate this by 45 degree. Okay. So, let me do that. Now, I am looking for a square whose, again the side lengths are unity, but now this square is rotated by 45 degree. So, now this, if you rotate 45 degree, you will get this, fine. And 45 degree, because we had studied that under axial loading, on the sections which are 45 degree inclined to this vertical, you will have maximum shear stress developed. I will just make that drawing here, so that if somebody does not remember, so if this is P and this is P, so then what happens is, if I go to if I look for an area which makes an angle theta, then the shear stress which acts on that surface is P over A. If this is having an area of A, say this area is A, so then P over A cosine of theta sine of theta, and the normal stress which acts on that plane is P over A and cosine square theta, and the tau max which happens at theta to equal to 45 degree, when this angle is 45 degree, and that is P over 2A, and at the same angle your sigma value at theta is 45 degree, sorry I hate this, is also P over 2A. So, this is just a summary of an earlier discussion. Anyways, so and then for this reason that maximum stress, shear stress is happening at 45 degree, we have tilted this cube by 45 degree, fine. Now, if we apply this load P, what will happen? So, this one will now be elongated in this way, right. So, fine, right. So, now what we will do, the concept of this derivation is to correlate these two deformations, and from there we will get the relationship between them. Okay. In order to do that, just think about this tilted or the rotated square can be thought of on the same picture here. I'll draw with a different color. You can just think that it's here, right. So the diagonal of that square is like these surfaces, because you remember everything is under the condition that this shrinks to size 0, right. So in such cases the exact location actually will be shrinking to that particular point. You can think of like this, or in fact if you have drawn like this, you can think of the other part like you have like this. Anyways, fine. So this viewpoint will be useful in deriving the expression. So I am just going to draw that now. So consider that portion of the rectangle. So now I am looking at this portion of the rectangle. Okay. Now what will happen to this rectangle portion here? It will be elongated in this direction, okay, and it will be shrunk in this direction, right? After you apply the force, initially this angle obviously was 45 degree, and now it will be some other angle which is less than 45 degree, okay, and initially this full angle was 90. So now this has, I'll just draw the as a dotted one, so that, sorry, the bad drawing, yeah. So earlier it was like that, and now it has become something like this. Then if you remember the definition of shear strain, the angle by which a 90-degree angle been reduced, okay. So now earlier it was 90, now it has become, say, 90 minus gamma max. It's gamma max because at 45-degree angle maximum shear stress will happen, so maximum shear strain also will happen, and that means this angle, the half angle will become 45 degree minus gamma max over 2. Okay, fine. But now what are these lengths now? These new lengths we have shown here to be what? This length has become 1 plus epsilon x, right? The new length has become 1 plus epsilon x. So this is 1 plus epsilon x, and this height has become 1 minus nu. So this height has become 1 minus nu epsilon x. Okay. So that means now what we can do is we will write, say, this tan of 45 degree minus gamma max by 2 is nothing but 1 minus nu epsilon x over 1 plus epsilon x, right? So that's one of the relationship which we get, and from the other one what we can do is, yeah, so from this expression we can also write that it is nothing but tan of 45 minus tan of gamma max by 2 over 1 plus tan of 45 times tan of gamma max over 2, right? But then we always tell that our deformations are very, very small. So that approximation, if you put, okay, I'll just put, so this expression we have got from this geometry, and this we have got from this. Okay, so these are two ways of calculating the same thing. Okay, so that means now I can write something here, those expressions. So 1 minus nu epsilon x by 1 plus epsilon x is equal to, under the limit that gamma max is very small, so tangent of that angle is the angle itself, and tan 45 degree is 1. So I will get something like 1 minus say gamma max over 2 by 1 plus gamma max over 2. So from here I am just trying to calculate gamma max. So that means so this minus this over this plus this. If I do, so what shall I get? Implies this will be say gamma max this minus this if I do over 2, right? No, sorry, is it so? Yeah, so in the denominator it will just be added up, so they will cancel, so it will by 2. So this is equal to this minus this will be epsilon x plus nu epsilon x over this plus this if I do, so 2 plus epsilon x minus nu epsilon x, right? Which is nothing but I can say that epsilon x times 1 plus nu over 2 plus 1 minus nu times epsilon x. That means I can say that your gamma max is equal to epsilon x times 1 plus nu over 1 plus 1 minus nu over 2 epsilon x, right? But then you see this term epsilon x itself is small, and then nu value ranges from say 0 to 0.5. So that means this value is always less than half, and then a small value multiplied with 0.5 maximum will always be very small as compared to 1. So what we can do is we can neglect this term as compared to this. So in approximation we can simply say that it's 1 plus nu times epsilon x. Okay, so gamma max we got like this. So we will say gamma max is equal to nothing but 1 plus nu times epsilon x, right? But then gamma max I can write as what? If I relate gamma max to tau max like with respect to g, and if I substitute that here, what I'll get is say tau max over g is 1 plus nu times epsilon x. Okay, so okay, I'll write epsilon x. But you see here, I think in the previous slide, yeah. So tau max is p over 2a. Okay, so just here tau max is p over 2a if a is the area of cross section, and your here epsilon x I can replace with again say 1 plus nu times say sigma x over e, right? Now sigma x is p over a because sigma x is the normal stress which exists on a normal plane. So now if you just see this, so that means your E over G is nothing but 1 plus nu times sigma x over tau max, which is nothing but sigma x over tau max. So you will get a 2 times 1 plus nu, right. So implies that if I now can write the final expression to be my shear modulus G, G is nothing but E over 2 times 1 plus nu. So this is the expression which we were looking for. Fine. So that's what is the expression which relates Young modulus of elasticity, Poisson's ratio, and the shear modulus. Fine. So that means now we know the complete relationship between converting from any two of the material property the other two. Okay. Great. So we'll stop here for this segment, and we will see the derivation of exactly the same relationship but from completely a different perspective. See you in the next segment.